Hello everyone, welcome to the first video in the video series on digital signal processing. In this video, we are going to go over the basics of signal processing. Let's start with the basic entities, signals and systems. Signal. A signal is a function or a medium which carries information. There are different types of signals like speech signal, music signal, ECG, image, video, etc. System. A system is used to define any process which takes an input signal and produces an output signal by working on the input signal. Signal processing is being widely used in various fields like machine learning, automation, communication, etc. to make the tasks more efficient and more simple. Signals are different types, like an image is a collection of pixels, whereas an EEG is a collection of electrical impulses in the brain. Signals also have different dimensionalities, like an image is a 2D signal, that is, it's a collection of 2 dimensions of pixels, whereas a video has another extra dimension to it, which is time. So video is a 3D signal. Systems are also of different types. There are systems which are used to cancel the echo in a room. There are systems which can filter out noises when you pass in an audio signal, and it gives out a clearer, amplified output of the audio. Signals are of two types, analog and digital. An analog signal is a continuous signal that contains time-varying quantities whose range is the real set, whereas a digital signal uses sequence of discrete values to represent data. Like computers uses the discrete value bits 0 and 1, and all the digits, letters, etc. are converted into bits 0 and 1 using the ASCII code. Just like we have analog and digital signals, we also have analog and digital systems. An analog system works on an analog input, whereas a digital system works on a digital input. Analog systems employ analytical techniques, whereas digital systems employ numerical techniques. Analog systems use analog electronics like LEDs, whereas digital systems use digital electronics like flip-flops, registers, etc. There is another class of systems called interface systems, like ADC and DAC. ADC stands for analog to digital converter, whereas DAC stands for digital to analog converter. These class of systems are used for cross-platform applications. The block diagram here shows us a basic analog signal processing system. What actually happens here is a physical signal is picked up by a sensor which is analog in nature. This signal is passed on to the signal processor, from which we get a desired output. This diagram here represents a digital signal processing system. In general, digital signal processing systems are much more complex when compared to analog signal processing systems. The reason being, most of the signals which are generated in nature, the signals we find in real life, are analog in nature, like audio signals and images. So, in order to work with analog signals, we first convert them to digital domain and do the required processing, after which they are converted back to analog domain. Now let's see how to convert analog signals to digital domain. We know that analog signals are continuous in both time and value domains. To convert it to digital, which is discrete in both, we use techniques called sampling and quantization. Quantization involves choosing levels in the value or amplitude domain and representing them as sequence of discrete values. whereas sampling involves picking out a few samples from the overall signal in the time domain. So how do we ensure that we sample the signal correctly in such a way that we don't lose the properties of the signal? Let's see. The Nyquist sampling theorem provides us with a good sampling rate, Fs. This theorem states that the sampling frequency Fs should be at least twice that of the maximum frequency contained in the signal. In mathematical terms, Fs sampling rate is greater than or equal to 2 times that of the maximum frequency contained in the signal. So what happens if we don't choose our Fs correctly? That is, what happens if our Fs is less than or equal to 2 times that of the Fc? Helps us. We have also seen about continuous, discontinuous signals, periodic and aperiodic signals. We have seen about different types of spectrums. Let's see. Let's start the discussion by choosing the example in the top left box. The signal here has a frequency of 1 Hz. From Nyquist sampling theorem, we get that Fs should at least be 2 Hz. That is, we have to pick up samples at every 0.5 second. What happens if we sample it at a frequency greater than Fs, say 3 Hz? We pick up more samples, which is not a bad thing. The more the number of samples we pick up, the better we will be able to reconstruct our signal back. But what if we sample at Fs less than 2 Fc, that is at a frequency less than 2 Hz? Say here we sample at 1.5 Hz, that is we pick up 2 samples every 3 seconds. When we try to reconstruct the signal back, we don't get the one from which we started. This is called as aliasing. Aliasing means that when you try to reconstruct a signal back from the samples, we don't get back the original one. Thus, undersampling leads to aliasing. This example here would help us understanding aliasing in a better way. The wave in the black represents the signal in which we are interested. The red dots represent the samples we have taken. The case here is that of undersampling. That is, Fs is less than or equal to 2 times Fc. We find that all the blue waves here on the screen pass through the given samples. So when we try to reconstruct the original signal back from the taken samples, we could end up with any one of them. This is called as aliasing. That is, when you try to reconstruct a signal back, it ends up different from the original signal. This happened due to undersampling, and because of undersampling, we were not able to capture the signal correctly. Here, we see how sampling is done in time domain. We multiply a given signal with a train of impulses, and we get a sample output. In frequency domain, what we do is we find the spectrum of the signal, and correspondingly we find the spectrum of the impulse train, and on convolving we get the frequency domain view of sampling. Here we also observe one more property, that is, multiplication in time domain is equivalent to convolution in frequency domain. Now let's see about LTI systems in convolution. LTI systems stand for linear time invariant systems. They obey the property of linearity and time invariance. Convolution is a process which we use to get an output from an LTI system. The output of a system y of t given an input x of t is defined as y of t is equal to x of t star h of t, which means on convolving x of t and h of t, we get the output of an LTI system. Here h of t stands for impulse response. Impulse response of a system is the output obtained when the input of the system is an impulse. Convolution arises as a consequence of LTI systems. Let's see how. On giving an input of impulse, we get impulse response as the output. As LTI systems satisfy time invariance, a shift in time would also reflect in the output. They also satisfy homogeneity property, because of which multiplication of a constant at the input will also reflect on the output. We know that integration is continuous summation, and when we try to integrate the input signal from minus infinite to infinite, it gives us the output y of t, which is nothing but convolution of x of t and h of t. For a system to be stable, it has to satisfy this condition, that is, on integrating mod of h of t dt from minus infinite to infinite, the output should be a finite number. Consider a room with an audio sound generator and a receiver. When an impulse is generated by the audio generator, the output seen at the receiver would be the impulse response of the room in the given configuration. Here, figure A shows the impulse response of the room. Essentially, it contains three components corresponding to different sounds received by the receiver. It involves the direct sound which is received from the generator, and then it involves the early reflections from the wall, and in the later part we see reverberation. We know that any signal can be expressed as a sum of sinusoids. This property is largely exploited by LTI systems to quickly find the output given an input. This is possible because sinusoids act as eigenfunctions of an LTI system. That is, given a sinusoid input, the output would be a scaled version of it. We know that eigenfunctions are the ones which, when operated using an operation t, give out a scaled version of the input eigenvector itself. Eigenfunction is similar to that of an eigenvector. When we pass an eigenfunction to an LTI system, we get a scaled output of the same eigenfunction. So, let's recap on how to find eigenvectors and eigenvalues of a given matrix. To find eigenvalues, we use the characteristic equation, which is A minus lambda times the identity matrix. Then, we equate the determinant of this to 0 and find the corresponding lambdas. These lambdas are the eigenvalues. To find the eigenvectors, we then use the eigenvalues which we obtained previously and solve the equation to find the general form of the eigenvector. For lambda equal to 5 and lambda equal to 2, we solve these equations in this case. And these are the eigenvectors which we have obtained. Why are eigenfunctions important? Let's see. If we can decompose a given signal into a sum of eigenfunctions, then we can use the following properties: the eigenfunction property and superposition property, to find the output of an LTI system. Let's see how. If a given input of an LTI system can be expressed as a linear combination of complex exponentials, the output can also be represented as a linear combination of the same exponential signals. This is because complex exponentials satisfy the eigenfunction property for an LTI system. So if you can do that for an input signal, then it becomes very easy to find the output. So here we have seen that using eigenfunction properties, the output of an LTI system can be quickly found. So how does going to frequency domain help us actually? Let's see. Here the harmonics AAA pitch produced is plotted as a graph of amplitude versus time. The below picture is the spectrum mapping of the above time domain signal. The signal, as we see, has frequencies in the range 500 to 1500 Hz, which are much visible. The harmonics are also present, but less in number. The color imaging is an indicator of the number of such frequencies observed in the signal, red being extreme and blue being low, meaning very few such frequencies were noted. Removing them would help us reduce the data to be transmitted or processed and gives us very small or no error when we try to reconstruct the original signal. Thus, we can do compression using frequency domain. Now, let's take up a problem. In the slide, we see musical notes produced by different means or instruments. Our task would be to identify the source of the musical note. The property which we are going to make use here is that each musical note has a unique fundamental frequency. The signal which we are using here, or the music note which we are taking into consideration, has fundamental period of 1/440 seconds. To solve this problem, first let's try out in the time domain. A simple method which we could use to do this would be the zero crossing based method. This method involves trying to find out the periodic part of the signal or the repeating part of the signal and trying to estimate its time period from which we can get the frequency. As we can see, this method works well for the first two but gives a bad result for the second two. One other way to do this could be to find all the possible zero crossings and plot a histogram of the periods obtained by doing such. We see that this has given us good results. Now, let's try to do the same thing in frequency domain. One method we could use would be to apply a Hamming window and then find the spectrum. Again, we see here that we get good results for the first two, but the results for the third and fourth are bad. To improve on this, in the frequency domain, what we do use is the substrum method. On using the substrum method, we get good results for all the four musical notes. Now, let's see the relationship between continuous time Fourier series and continuous time Fourier transform. Continuous time Fourier series is used to do frequency analysis of continuous periodic signals, whereas continuous time Fourier transform is used for continuous aperiodic signals. If we see in the first example, it's a periodic square wave with period t0 equal to 2t. And then, when we find the spectrum corresponding to it, the coefficients we get are such. Now, when we increase the period from 2t to 4t, what we see is that the coefficients come more closer. This is because frequency reduces as we keep increasing the time period. They start coming more and more closer, and after a point they seem to be like continuous ones. Thus, as the time period of the input wave keeps increasing, what we observe is that the Fourier coefficients keep coming more and more close and appear to be like a continuous one. Having a large time period is similar to having a time period which is very large or infinite, meaning the signal behaves as if it's an aperiodic signal, and CTFS converges to CTFT. This slide gives us an overview of all the transforms: CTFS, CTFT, DTFS, and DTFT. We know that signals can be continuous or discrete. They can also be periodic and aperiodic. The transform which is applied on a continuous periodic signal is CTFS. The one applied on a continuous aperiodic signal is CTFT. The one applied on discrete periodic signal is DTFS, while the one applied on discrete aperiodic signal is DTFT. The equations corresponding to the conversion of signals to spectrum domain and back to the original domain are represented here. Let's see the relationship between DTFS and DFT. DTFS is applied to find the spectrum of discrete periodic signals, whereas DFT is applied to find the spectrum of a finite discrete signal. The equations which represent the process DFT are as follows. Xk, the spectrum coefficients in DFT, can be found using this equation, and this equation is also called as the analysis equation. Whereas we could construct the original signal back from the spectrum domain using the synthesis equation. The relationship between the spectrum coefficient of DTFS and DFT is as follows. So in this video, we have discussed about signals and systems with a few examples. We have also seen how convolution arises as a consequence of LTI systems. We have also learned about eigenfunctions and how expressing signals as sinusoids helps us. We have also seen about continuous, discontinuous signals, periodic and aperiodic signals. We have seen about different types of spectrums like CTFS, CTFT, DTFS and DTFT of signals. We have also discussed the relationship between CTFS and CTFT and DTFS and DFT. Thank you for watching the video.